Hello, everyone, and welcome to today's presentation. I am your host, Scott Hartzall, and today's presentation is actually a follow-up from what we started with last month, discussing optimizing in-situ complex metals remediation through numerical simulations. This month, we have Melanie Beck is going to join with Jim Schutz to discuss some site-specific examples of putting this information into practice. Housekeeping items, we will try to keep phone lines muted so that we don't have background noise. If you have questions, you can enter them through the chat feature, or you can hold your question to the Q&A period at the end of the presentation, and we will unmute phones to be able to ask a question at that time. There is this session today has been approved for CEU credits, and there is a sign-in sheet in the chat section of the presentation. If you have trouble with that, you can always email me, and I'd be glad to get it to you after the presentation's over. With that, I'm going to turn it over to Jim and Melanie.
Thank you, Scott. As we normally do, we will start out with a core value moment. So the core value moment here today is related to diversity, inclusion, which we talk about in many different terms. I found this article interesting, and so I thought I would share it with the group today regarding cognitive diversity, which is a study of essentially how diverse lines of thinking create improvements in performance. So what this study looked at here, and this is from the Harvard Business Review, you can see different teams on the y-axis and different columns on the x-axis. And what they found was, based on cognitive diversity, teams were able to complete tasks with higher performance levels than teams that lacked cognitive diversity. And there's a couple of columns here that go over the details of the diversity itself and the way people think. One is knowledge processing. You see the standard deviation. What that is really a reflection on is how one might solve a problem and, let's say, consolidate and deploy existing knowledge or generate new knowledge when faced with a certain situation. And then the team also looked at perspective, which evaluates the extent to which individuals may prefer to deploy their own expertise or orchestrate ideas and expertise of others. So you can imagine how in the perspective column, teams with more diversity would bring a variety of ideas and a variety of problem-solving skills, and which is the reason why they outperformed other groups and other teams. And so I think this, goes beyond some of the abstract ways that we may talk about inclusion and diversity, and really shows from a respected study on how diversity and inclusion really does affect performance. So that's the core value moment. Before we get into the site-specific details of this Part 2 webinar series, I would like to take a moment to summarize Part 1. So in the previous webinar, we went over much of the fundamentals of arsenic concentrations and arsenic plumes as related to maybe natural and or anthropogenic causes. And we also discussed in detail a lot of the fundamentals of groundwater flow modeling and fate and transport modeling. So starting on the left here, we discussed a variety of important aspects of arsenic as it relates to the remedial industry such that we work in. One is plume duration, and we've known this, I think, as practitioners for a while, but it's becoming more and more explicitly detailed in the sciences on how plume duration for arsenic, dissolved arsenic, can sometimes be centuries. It has a very low MCL in respect to the concentrations that we often see it in, and that, supports the duration as well. There's a few different types of sources when we talk about arsenic, which can often make it a challenge. Obviously, there are anthropogenic sources, let's say from chemical manufacturing, but there can also be naturally occurring arsenic sources, or a combination of both, in which an anthropogenic source of, let's say, a volatile organic carbon plume may dissolve arsenic from natural sources and create a plume that would not be there otherwise and has no direct arsenic concentrations from, let's say, the manufacturing process itself. Furthermore, distribution, it can migrate and disperse. And one of the challenges with arsenic is that things change over time. And oftentimes there may not be the same equilibrium that we can assume for other dissolved contaminants. We also discussed fate and transport biogeochemistry, how that is also generally variable in time and space, depending on where the source is and how the source may be creating the dissolved phase plume of arsenic. And we discussed how even those change both in time and space, and native versus plume redox conditions, where sometimes we have native carbon sources and sometimes we have anthropogenic carbon sources, like I spoke about a moment ago. And we went into some of the details on how there can be arsenic cycling related to ORP changes and or pH changes as the result of changes in redox and the scavenging minerals, and how that interaction is important to the fate and transport biogeochemistry. Lastly, on the arsenic side, we really went into in-situ treatment options beyond, obviously, pump and treat, which is often a good containment system, but not often a good long-term treatment. So, many practitioners have looked at PRBs, and here at Parsons, we've looked at several different technologies, which we're demonstrating today. One of those is a full plume treatment. We're currently working on the pilot test for that full plume treatment, which we'll discuss throughout this webinar. And then moving over onto the right side here, after I discussed a lot of the minutiae details on arsenic and some of its complications, why we may see it, why it's hard to treat, then there was a very fundamental discussion on fate and transport of groundwater plumes and how to correctly model that. We started with groundwater flow modeling and how numeric modeling is a very good tool for that. We really came to a conclusion at the end with the concept that if we're looking at a sulfate treatment for an arsenic plume, we know that sulfate is highly consumed in an anaerobic environment. That's part of the reason that we're looking to use sulfate for treatment of arsenic. But in order to successfully simulate the fate and transport of a sulfate injectate, we really need to look at the fate and transport part of the equation. And you can see that in the lower part of the upper right side of the screen, where we have the chemical reaction term. We need to really apply that chemical reaction term because sulfate is so highly consumed. And therefore, fate and transport modeling must be applied if we're going to have a successful simulation of a sulfate injection for treatment of arsenic. Because while we may normally try to keep things simple and look merely at groundwater flow and groundwater flow velocities, and do our injection design based on those velocities and travel times without accounting for this high consumption, we may overdose the situation and have sulfate beyond the area of interest. Or conversely, we may underdose the pilot test and see very little or no treatment at all because of the distance to our monitoring wells, which would give us a failure of a pilot test, even though we know the chemistry actually works. So with that, we decided to, in designing our pilot test, do fate and transport modeling in order to really hone in on what is the concentration, how long is it going to take to inject, and what should we expect in terms of breakthrough of the sulfate. Next slide. So I'll go through the agenda here quickly. We'll go through the site background and remedial approach. We'll do a bit of the modeling overview, talk about the static groundwater flow model that was developed, and then a pumping groundwater flow model that was developed, both calibrated in order to support the final end product, which is a fate and transport model for sulfate injection into arsenic plume. Next slide. Site background. So this is the Baird and McGuire Superfund site. It's a former chemical mixing and batching company from the late 1900s. It's in eastern Massachusetts. And you can see on the image here, it's a typical northeastern topography and, somewhat developed area. The waste were disposed in direct discharge to the soil. There is a nearby brook and wetlands and a former gravel pit. The geology is glacial deposits. There's a small stream valley that flows through the area of interest and adjacent to the impacted soils. Groundwater and soil concentrations of concern. There's dissolved hydrocarbons, and those are actually creating an arsenic plume. So we have arsenic, dissolved hydrocarbons, and then LNAPL, i.e. light non-aqueous phase liquid, which is also part of the overall remedial strategy, is to clean that up with sulfate injection. There's a potential receptor, and that's the down gradient river or stream. The program, the project has been in groundwater recovery and treatment for many years, going back to 1993. So there's been a very active and effective groundwater recovery system, i.e., capture and treatment, pump and treat system. And it's done a very good job over the years. But in looking forward, in terms of how long is this plume going to last and how long do we need to contain the plume before it goes away? When Mass DEP took over the project, they started thinking about these things. And more recently, we've put together a plan and approach and are now conducting that approach in terms of pilot testing to be more innovative and get out of pump and treat and actually use in situ remedial strategies like we may use at other types of sites, but apply that very specifically to not only the hydrocarbon and the non-aqueous phase liquid, but create the correct redox conditions such that the arsenic is then essentially precipitated out and binds to iron and becomes a non-issue in terms of groundwater contamination. Next slide. So quickly, we went over this a little bit last time. This is really an approach that Parsons has developed in the past for a patented technology that we call NAPLOA. And again, it's using sulfate to create the correct biogeochemical conditions for NAPL, but in this case, we're using it to tweak the geochemistry so that we're able to revert the dissolved phase arsenic and get that to bind and sequester to iron in the soil and come out of the dissolved phase, i.e. reduce the concentration of arsenic through sulfate injection. And you can see on the lower left a nice pyrite crystal. So iron sulfide is one of the key components of this biogeochemical reaction, and one of the reasons that we're able to change the groundwater conditions and remediate arsenic with a sulfate injection. Next slide. So in big picture concept, we're talking about a sulfate plume, an arsenic plume. We inject sulfate into a series of injection wells, and we extract down gradient, recirculate the water back up to the injection area, add sulfate, and create this recirculation system so that the sulfate itself in dissolved phase can migrate down gradient. And as it migrates down gradient, it treats the arsenic with sulfide minerals and hydrocarbon biodegradation. Next slide. Pilot test objectives. So here you can see the sulfate area that we're doing the pilot test in. The black line represents the real plume area that we want to treat, and then the red line represents some of that fringe area. The idea for this pilot test is to really hone in on the center of the plume and the center of the LNAPL area where the arsenic exists. And you can see the groundwater flow arrow, not only through natural groundwater flow, but the small circle on the lower right represents the extraction well. So we're trying to create the sulfate plume such that it migrates down gradient through the arsenic and the LNAPL plume. Next slide. And so this all brings us to the numerical groundwater flow model and fate and transport model, which was developed, calibrated, and sensitivity tested such that we can understand what concentration should we inject, how long should we inject it, and what are the expectations of the breakthrough of the sulfate. And with that, I'll pass it over to Melanie Beck.
All right, thanks, Jim. Sorry, thanks for that, Jim. I'm going to start with discussing the steps taken to develop and calibrate the numerical flow model. The numerical flow model was used to create the fate and transport model to simulate the pilot test scenarios. All right, so this is a model process diagram that represents all of the steps taken in developing the numerical flow model before arriving at the final fate and transport model. So I'm going to break this out and piece by piece to go over what exactly was done at each step. So beginning with the data inputs into the model, we start with, we were fortunate enough to have aquifer testing for this site, specifically a pumping test. Many contaminated sites have logistical constraints when it comes to performing pumping tests due to the large volumes of extracted water that you then have to treat before disposing. So often it just is too costly in order to perform a pumping test, and most clients will go for a slug test instead. A pumping test represents a more larger scale hydraulic conductivity value, whereas a slug test only represents a small area around the monitoring well itself. But luckily, we have an ongoing pump and treat system at the site, and so that logistical constraint of dealing with the extracted water is already handled, and so therefore we were able to perform a pumping test in which we shut down the active extraction wells and monitored hydraulic heads through the use of pressure transducers over a period of time while extracting a known flow rate. And so we were able to use this pumping test to evaluate the hydraulic conductivities at the site and get a tighter estimate of the range of hydraulic conductivity for inputs into the groundwater model. In addition to the aquifer testing information, we used regional information. The regional information includes data such as weather data or precipitation, soils data for estimating runoff conditions, and regional geologic information and topography. We also had a CTEK model, which was provided to us by the client, A CTEK model I'll go over in more detail on a later slide, but essentially was a complex geologic model in 3 dimensions, and we are able to use that to import and build the ModFlow numerical model, specifically representing the different geologic zones. So now that we have the model structure developed and built, the next step is to do initial runs and testing. This step involves adding in boundary conditions and parameter values and running the model to ensure that there are no numerical stability issues and that we're achieving a good water balance and good convergence. This is usually just a very initial step, and it's just to make sure that the model is doing what you expect it to do and that you're getting conditions similar to what you observe on site. We started with a static conditions model, static conditions meaning non-pumping conditions. And for this, we shut down the extraction wells for a period of time and monitored hydraulic heads until equilibrium was reached, meaning hydraulic heads were no longer rising as a result of discontinued pumping. And once we reached these static conditions, we then performed a site-wide synoptic monitoring event for hydraulic heads, and we were able to use that data for groundwater calibration targets in the model. So once we have the model running and having good convergence and a good water balance, we then move on to manual calibration. Manual calibration is trial and error, changing parameters slightly and observing the effects on the groundwater model calibration. Once we achieve a good manual calibration, we then can use PEST, which is an automated estimation software used with ModFlow that essentially takes the parameter ranges and parameter value combinations and optimizes the combination to achieve the best calibration statistics. PEST runs the model thousands, if not tens of thousands of times, depending on how many parameter values there are and potential ranges of parameter values. And it attempts to minimize the objective function. In this case, the residual sum of the squares, or model residual being the difference between the simulated head and the observed hydraulic head. The lower that residual, the better the calibration. And so PEST optimizes that calibration process. And usually the manual calibration might go back and forth with PEST to achieve the best calibration result while also maintaining realistic parameter combinations. PEST also provides sensitivity values. So a parameter sensitivity, a sensitive parameter is one in which a small change in the parameter value results in a large effect on the calibration statistics. Sensitivity testing is always an important step to take during the modeling process because it informs the uncertainty of the model. If you have a very sensitive parameter, one in which it has a large outcome on the calibration and a large range in that parameter value, if that parameter value is actually different than what is estimated or calibrated, then that could have a large effect on the rest of the model calibration and all of the other model parameters. And so it's very important to understand which parameters are most sensitive and take that into consideration when interpreting model results. For this model, we built it using ModFlow 2005, which is it's a ModFlow version that's been around for a long time. It's widely used. But then we also used the Newton solver as part of the ModFlow 2005 package. And the Newton solver is relatively new and handles numerical instability issues better than some of the previous ModFlow versions, specifically in relation to large gradients, which was appropriate for the site since we do have a very large gradient across the direction of groundwater flow. Once we had achieved a manual calibration for the static conditions, we then developed a pumping conditions model. The purpose of the pumping conditions model was both to further corroborate the static conditions modeling parameters, but also to evaluate the current capture effectiveness of the ongoing pump and treat system. The The pumping conditions model can further corroborate the static conditions model because we're adding an additional known input into the model, as well as adding additional stress to the aquifer itself during the modeling process. And this helps to inform even more what the parameter values are within the region surrounding the extraction wells. In order to develop the pumping model, we took the static conditions model and imported the pumping wells, and then changed the monitoring wells or the groundwater calibration targets to be a synoptic event from pumping conditions in which the extraction wells had been running long enough and to achieve equilibrium conditions, and that water levels are no longer dropping as a result of pumping. And we use that synoptic-wide pumping conditions monitoring event to calibrate the pumping conditions model, just as we had calibrated the static conditions model. Once we had a fully calibrated pumping conditions model, it was then important to have the static conditions model and the pumping conditions model agree with each other. And so we went back with the new information gained from the pumping conditions model and updated the static conditions model so that the two models agreed with each other, the only difference being the pumping wells and the pumping condition model. And the static conditions model, we then moved forward and developed a fate and transport model in order to test the pilot test scenarios. To develop the fate and transport model, we switched to using ModFlow USG, which is a relatively new version of ModFlow. Its main attraction is the use of unstructured grids, which is what USG stands for. And I'll go over unstructured grids a little bit more in another slide. But ModFlow USG also has its own fate and transport solution, very similar to MT3DMS, which most modelers will have heard of that. But that's just another fate and transport modeling code that can be used with ModFlow. Okay, so now that I've gone over the entire process, I'll start by talking about the input parameters and boundary conditions. So this is a slide that represents the boundary conditions used in the model. We're looking at a plan view of the groundwater model itself. Within the blue box in the middle is the area of interest. The purple line represents the extent of the dissolved phase arsenic plume. Each blue circle with an X is an active on-site extraction well. And the turquoise line that runs through the extraction wells is an ephemeral brook that turned out to be very important to calibration. That ephemeral brook, when it has water in it, is a losing stream and had a large effect on the groundwater conditions at the site and specifically the groundwater capture when there is water in that brook. The green line that runs through the area of interest is the site river, which is also the receptor for the contamination, or potential receptor, I should say. Upriver, there is a general head boundary, which represents the upgradient lake, and then downriver is another general head boundary, which represents the downgradient lake. On the west and east sides, very far away from the area of interest, greater than 5,000 feet, is general head boundaries, which induce a gradient from the west to the east, as observed at the site. Okay, so this is another plan view of the same model, and this is to demonstrate the grid discretization. The grid telescopes from 500 feet by 500 feet to 10 feet by 10 feet. Telescoping is a very useful way to balance numerical efficiency with model precision. Within the area of interest, it's important to have a grid size that's small enough in order to estimate an appropriate area of interest. So if an extraction well only has a radius of influence of 20 feet, you wouldn't want your grid size to be larger than 20 feet and risk over-representing the radius of influence for that extraction well. Similarly, if you had a river that was only 10 feet across, you wouldn't want your grid size to be larger than that 10-foot wide river, and again, misrepresent capture or flux into the river. And so it's very important to have grid size small enough within the area of interest so you can achieve the model precision that you need for the questions that you're trying to answer with the groundwater model. However, outside of the area of interest, it's not as important to be as precise, and so the grid size can be quite larger. And so it's useful to have a larger grid size outside of the area to reduce the amount of cells or nodes within the grid discretization itself. You can imagine that if you had a 10-foot by 10-foot grid size over a mile and a mile wide domain for 5 or 6 layers of a model, that turns into many grid cells, which can turn into hours of computation time just for one model run, let alone the thousands of model runs you do during sensitivity testing. And so telescoping is a great way to balance that numerical efficiency while also achieving the precision that's necessary. As I mentioned, ModFlow USG this model was originally developed with ModFlow 2005 and then transitioned to USG, so we did not transition to an unstructured grid. However, we could at this point, since we are using USG, switch to an unstructured grid in that instead of telescoping, we can just have the larger grid size outside of the area of interest and a nested grid inside the area of interest of the chosen grid size. And that sort of reduces some of these awkwardly sized grid cells that result from the telescoping outside of the area of interest. So we were provided a CTEK EBS model. CTEK EBS is a geostatistical software used for creating visuals of complicated geology at sites, but also for estimating the extent of plumes in three-dimensional space. This EBS model was specifically for the site conceptual model representing the complex geology at the site. And it's based on the boring logs and well logs, that information from the site. We were able to use this data, the CTEK model, and export from that the elevations of the different geologic layers and import that into the groundwater model. Over here, you can see a cross-section across the area of interest showing the undulating surfaces that represent each of the model layers. Some changes that we made between the CTEK model and the groundwater model where we simplified and reduced the geometry relative to just the conductive zones. We didn't need quite as fine geologic resolution as we had in the CTEK model because we were mostly just interested on where the hydraulic conductivity values would differ. And then additionally, rather than explicitly simulating pinch-outs, we simulated them using relatively thin layers and discretizing different hydraulic conductivity zones in that region. And this was mainly for numerical stability. ModFlow doesn't usually handle very thin layers or pinch-outs very well. So as I mentioned, we use hydraulic conductivity zonation to represent the pinch-outs, and then additionally the other geology at the site. So this is that same cross-section, but with the hydraulic conductivity field shown. This top layer here is ash. That's from a previous remediation in which site soils were excavated, incinerated to treat VOCs, and then relayed at the site. The ash overlies a medium to coarse sand. This medium to coarse sand has a relatively high hydraulic conductivity and is where the majority of the existing site contaminants are in the dissolve phase. Intermixed with the medium to coarse sand are lenses of gravel or layers of gravel and supported by several boring logs. This gravel has an even higher hydraulic conductivity relative to the coarse sand. Underlaying the river is a silt zone. Silt has a relatively lower hydraulic conductivity, and this proved to be very important to the groundwater modeling calibration, but also the pilot testing scenarios. And I'll explain why in a later slide. And the site overlays glacial till and a granite bedrock. And this is to show that our groundwater model cross-section had very good agreement with this site engineering geology cross-section. Okay, so now that we have the model completely built, we're on to the point of which we can start to calibrate. This slide represents the final calibrated parameters for the initial static conditions model. And the main point of this slide is to demonstrate that the parameters did not change much between the initial parameter values and the final calibrated parameter values. And that was done intentionally to make sure that parameter values were in line with what previous estimates provided, but also literature values as well. Okay, so this is what we call a one-to-one plot. On the x-axis is the observed hydraulic head values, and on the y-axis is the simulated hydraulic head values. And that blue diagonal across the plot represents the one-to-one line, in which if we perfectly simulated all of the hydraulic heads, the data points would fall along that line. The goal during calibration is to get a good scatter across that line to show that we're not overestimating in some areas the hydraulic heads or underestimating in other areas systemically, so that we can actually change things and get a better calibration. And we're hoping to achieve a good scatter across the entire range of data values. So as you can see from this plot, we had a very good agreement between simulated and observed hydraulic heads. We also look at the general statistics of calibration, and these are all statistics on the model residuals, which are, again, the difference between the observed and simulated hydraulic heads. And we ended up with a scaled root mean square error down here in the red box of 0.037, which indicates very good agreement between the simulated and hydraulic heads. The scaled root mean square error is this root mean squared error divided by the range in observations. And it's a statistical measure used to evaluate the calibration of the model. Okay, so now we have a fully calibrated static conditions model. So we're at the point in our process where we moved on to a pumping conditions model. And again, we developed this pumping conditions model to further verify the static conditions model, but also to evaluate the current effectiveness of the pump and treat system. So in order to do this, we imported the pumping wells with the steady state daily pump rates. These are provided over here, and they were provided to us by the operations team. It was understood from the operations team at the site that there was some uncertainty associated with these flow rate estimates. That's very common for the flow meters that we see on site. So we included the flow rates as another calibration parameter due to the uncertainty in the known value. We additionally imported water level measurements from the pumping event from the same wells used for the calibration of the static conditions model. Additionally, we added a recharge zone. So all of the all of the water extracted on site is then put back into the groundwater through the use of recharge basins. And so for a good water balance, all of the water extracted from the wells in the model was then input back into the model at these recharge basins. We added an evapotranspiration zone down gradient of these recharge basins to represent increased ET as a result of the increased water influx. And additionally, there is a marshy area in that area that indicated to us there may be increased ET as a result of these recharge basins. Okay, so just as we did for the static conditions, we calibrated the pumping conditions. So this table over here shows how the parameters changed again between the static conditions and pumping conditions model. But all of the parameters still stayed in line with original estimates and literature values. And I mentioned we additionally included the flow rates from the pumping wells in the model calibration itself. And as you can see, some of the flow rates did change substantially between what was estimated and what was calibrated. This is the one-to-one plot for the pumping conditions model, again demonstrating that we had great agreement between the observed hydraulic heads and the simulated hydraulic heads, and a scaled RMS value of 0.043, which is just slightly above what we had achieved for the static conditions model. Okay, now we're at the point in the process where we've now fully calibrated a pumping conditions model and fully calibrated a static conditions model. And so we go back to the original static conditions model to make sure that the two models agree with each other. So we took the parameter values that we changed from the pumping conditions model and updated those in the static conditions model, and then recalibrated. Following that recalibration, we resulted in this one-to-one plot and resulting calibration statistics. The scaled RMS had increased slightly from the original static conditions model to the final static conditions model, but we still had very good statistical calibration and better confidence in our estimated hydraulic parameters from the pumping conditions model. So as I mentioned, it's very important to do sensitivity analysis during the modeling process. So on these plots, on the x-axis are each of the parameters, and on the y-axis are the relative qualitative sensitivities for comparison. From the static conditions model, the most sensitive parameters were the regional recharge value as well as the hydraulic conductivities. We then reran the sensitivity analysis for the pumping conditions model, and that resulted in very different parameter sensitivities. Mainly the pumping wells were the most sensitive parameters. This makes sense because the extraction wells are very close to many of the observation wells and groundwater calibration targets, and so those should have a very large effect on the calibration statistics, but also because they're an additional stress on the groundwater or on the aquifer itself. In addition to a statistical calibration, we also always do a visual calibration, and that's to make sure that the groundwater contours generally agree with the same shape of what we observe from the observed hydraulic head contours. And so that's what we're viewing here. In each of these plots, there's darker brown lines, which represent the simulated groundwater hydraulic contours, hydraulic head contours. And then the lighter yellow lines represent the observed hydraulic head contours for both the static and pumping conditions. And as you can see, we have generally good agreement between the contours for both the static conditions and pumping conditions, and that the shapes are similar and groundwater flow is going in the same direction. We developed this pumping conditions model for evaluation of the current pump and treat system to see if the target treatment area was primarily being captured. And we did this through the use of particle tracking. So these are particles tracked in reverse from the pumping wells, so we can see what coverage of groundwater extraction are we achieving in capture. And you can see here from the static conditions that without the pump and treat system, all of the water flows to the receptor, the river. And so the pump and treat system proved to be effectively capturing the target treatment area. That being said, we know that in order for this to continue to be effective, it would have to run for a very long time. So a more innovative solution is needed to effectively treat in a shorter time frame. Okay, so on to the fate and transport modeling part of the presentation. So I'll discuss the development of the fate and transport model and then the results from the pilot testing design optimization. Okay, just to go over the pilot testing design once again. So we were told to assume 8 injection wells with an injection rate of 1 GPM or 1 gallon per minute for each well. So a total injection rate of 8 gallons per minute. This yellow line represents the target treatment area, which is the residual hydrocarbon plume. Again, we're trying to treat the residual hydrocarbon plume to hopefully create conditions that can sequester the dissolved phase arsenic. We were asked to determine the optimal injection well spacing in order to get the most coverage of the existing residual hydrocarbon plume. And we put a target treatment distance of this line in order to achieve concentrations above 50 milligrams per liter of sulfate while avoiding concentrations above 50 milligrams per liter of sulfate at the river. So we wanted concentrations above 50 milligrams per liter to this line, but not past it. This purple line here represents an extraction well, which would be used to supply the injection well water. So this extraction well will extract at the same rate that injection wells are injecting. So to develop the fate and transport model, we started with the injection and placing the injection wells and extraction well into the model. And first, through the use of particle tracking, we looked at what the optimal injection well spacing would be. In addition, and we did this through the use of particle tracking, both to get an idea of average linear velocities and transport times, but also what coverage could we get with this spacing. Once we had determined the optimal injection well spacing, we then input concentrations into each of these injection wells. And part of what the fate and transport modeling was designed to evaluate was what is the optimal injectate concentration. And then for the sulfate degradation parameters, we use site bench scale testing in order to determine what the consumption of sulfate would be at the site. I wanted to touch on an important update that we made to the numerical groundwater model during the pilot testing design. And this involved the upland pinch out of the sand zone. So in these plan views here, this represents the line between where the sand, this dark red color, pinches out to the bedrock, this lighter pink color. And we had previously estimated this based on boring logs, but with new information during the fate and transport model, we realized that the pinch out was further up gradient than we originally assumed. And this was actually something that had no effect on the model calibration. And so it was something we didn't pick up on until we are placing the injection wells in the model. And this was, while it's not important to the groundwater calibration, was very important to a successful pilot test design, because the goal was to have the injection wells as far up gradient as possible while not encountering this low hydraulic conductivity bedrock. The higher hydraulic conductivity sand is both where the dissolved concentrations are and will allow for higher injection rates and travel times. And so it's very important to make sure that the injection wells were designed in locations where higher injection rates could be achieved. And this is just an important thing to note, just one side effect of groundwater modeling, and that you can gain more information about the site and a better site conceptual model for assisting in design. Site bench scale testing was performed in order to determine the decay rate for sulfate. So bench scale testing, meaning that site samples were analyzed in a lab. So each one of these plots on the x-axis is time in days, and on the y-axis is sulfate concentration. This first plot is for first order decay, and the second plot is for zero order decay. We ended up using the first order decay solution or estimation of decay rate, and that resulted in an average half-life of 77 days. That being said, we were given a large range of sulfate half-lives from the testing and literature values, and so we wanted to consider that range during the entire modeling process to make sure that we understand how half-life affects the sulfate transport. So that range was from 30 days to 190 days. To evaluate the injectate concentration, this is a plot that first represents different concentrations for a half-life of 77 days. Each line series is a different injectate concentration, blue being 1,000 milligrams per liter, gray being 250, and orange being 500 milligrams per liter. On the x-axis is distance along the sulfate plume center line, and on the y-axis is concentration of sulfate in milligrams per liter. This yellow line represents our target treatment distance, while the green line represents the site river. From this plot, it seems that we reach a target concentration of 50 milligrams per liter while avoiding those concentrations above 50 milligrams per liter at the river, with an injectate concentration of 1,000 milligrams per liter. That being said, as I said, we do want to look at all the range of half-lives. So 77 is much smaller than the highest estimate for half-life. So we wanted to consider that as well when determining the optimal injectate concentration. So these are similar plots in that on the x-axis is distance and on the y-axis is concentration of sulfate. Each plot represents a different injectate concentration, and each line series is a different half-life. So I can just bring your attention to down here for 1,000 milligrams per liter. As you can see, concentrations were above 50 milligrams per liter at the river for a half-life of 190 days. Due to this result, we recommended an injectate concentration of 500 milligrams per liter in order to ensure that we're protecting the river regardless of the half-life of sulfate. Okay, this plot represents on the x-axis we have distance, and on the y-axis we have days. Each data point represents the time to reach steady state conditions for the sulfate transport. Steady state meaning that at this distance, concentrations are no longer increasing because the transport has sulfate is equal to the degradation of sulfate or consumption of sulfate. And the main purpose of this plot is to get an idea of how long the pilot testing will take. And so each one of the line series represents a different half-life, so we can get an idea across the entire range of half-lives how long the pilot testing would take if this were the half-life that we found in the field. And then each of the text boxes represents the concentration of sulfate at milligrams per liter at that steady state condition. And so as you can see, for a half-life of 77 days, we can expect the pilot test to last about a year in order to achieve that target distance, at which point concentrations are at steady state and it's no longer necessary for continual injection. Okay, so these are plots that represents the final results of the fate and transport modeling. These two plots are cross sections along this A to A prime line, and the bright colors represent sulfate concentrations shown only above 50 milligrams per liter. In general, we found that 8 injection wells injecting at 500 milligrams per liter at 1 GPM covered approximately 80% of the target treatment area in aerial view. When looking at the cross section, an important thing to note here, this silt zone, which I demonstrated earlier on the hydraulic conductivity zones under the site river, actually proved to be protective of the site river for sulfate concentrations, and that the lower hydraulic conductivities reduce the average linear velocity enough in which the sulfate consumption could overcome the sulfate transport. And so the silt zone proved to be very important to the pilot testing in general, allowing for concentrations of 500 milligrams per liter to be injected. Okay, as I mentioned earlier, sensitivity testing is an important part of the process. However, for sensitivity testing for this analysis, we don't have results to calibrate to. And so in order to calibrate, we looked at how changing parameters affect the actual extent and transport of sulfate in order to test which parameters are most sensitive. So in order to compare results between parameters, we compared the coverage of the sulfate plume at or greater than 50 milligrams per liter, that overlap with the existing residual hydrocarbon plume. So that's what this figure is representing here, and that this line is the residual hydrocarbon plume, and each one of these colored lines represent a different half-life, and the extent of sulfate for that half-life at 50 milligrams per liter, and the solid color being the overlap between the two plumes. And this percentage of the total plume area was what we used to compare between results. So over here on the x-axis, we have percent change in the parameter relative to this baseline scenario, and then percent coverage of the NAPL plume within the target region. And the way to read this plot is a larger slope represents a more sensitive parameter, and that a small change in the parameter value resulted in a large change in the parameter results. So the most sensitive parameters from this analysis proved to be the hydraulic conductivity of the sand unit and the half-life of sulfate. Longitudinal dispersivity proved to be relatively insensitive, and this could be due to the high average linear velocity at the site, resulting in a more advection dominant flow regime as opposed to dispersion being more dominant. Okay, so in conclusion, results of the flow model improved the hydrogeological information of the site, including the importance of the upland sand pinch-out zone, as well as the alluvial formation and its relevance to groundwater flow patterns. The model also revealed important spatial patterns for the silt near the site river and its importance to the pilot test design and being protective of the river. More broad general conclusion from this modeling is that numerical modeling is an effective tool to assist in the optimization of not just remedial design, but also pilot testing design and ensuring that you have an effective pilot test to actually test whether or not the treatment technology is effective. Further work will include field corroboration. We're currently doing the pilot testing in the field and getting data as we speak. So further work will include field validation using that data so we can update the model to be used for hopefully the remedial design. I just want to take a moment to acknowledge both my coworkers and the client. So Julian Chimbert, Jim Shaw, Glenn Ulrich, and Paul Feshbach-Marini are my coworkers working on the site and Mass DEP. I'd like to acknowledge them for taking such an innovative approach to this site. Okay, so these are the CE credit questions. I don't know if I should read them or if we should just go over them in general. Suppose I'll just go over them. What was the model code used for the fate and transport model? A, finite element, B, modful USG, or C, MT3DMS? Suppose people can answer in the chat or unmute themselves and answer.
For those that have have downloaded the attendance sheet, it's also on the attendance sheet, a place to put the answers in.
Does anyone want to try to answer that question? I don't know if there's chats coming in. B, correct me here. 2, what was the optimal injectate concentration for the pilot test as determined by the modeling analysis? A, 500 milligrams per liter, B, 200 milligrams per liter, or C, 50 milligrams per liter? Yeah, A. In what ways does numerical modeling assist in situ pilot testing? A, injection rates, B, injection well placement, C, time of substrate travel, or D, all of the above? Yep, C. All right, and at this point, I'll open it up to Q&A if anybody has any additional questions or wants any more clarification. Mahir.
Hey, Melanie and Jim, this was amazing. I had one question is, had you guys not done this modeling, where would without this modeling, the insight you guys gain, what would the team would have implemented pitfalls, and was there a risk reduction for the client and cost savings that was realized for the client?
Yeah, I'll take that. Thanks, Mahir. There was both a cost savings and a risk reduction based on the fact that sulfate has a very complicated transport rate, and the injection design team, without having a complicated model, would have been forced to use very simplistic approaches and could have very significantly overestimated or underestimated not only the concentration, but the injection time, and which could have resulted in impacts to the stream, which, obviously be an undesirable effect, i.e. sulfate making it to the stream above the surface water criteria. Comparably to heavy of a injection sulfate concentration over a short period could have, precipitated out the iron and arsenic too quickly and caused formation clogging. So I think there's a variety of ways that the numeric modeling helped with the injection design itself and saved cost. And over the past decade, we've developed a variety of types of in-situ injection models, but they are typically like flow models, which can really help in terms of how many wells do you need, how far spaced should they be. But in this case, because of the sulfate decay rate, we really needed to look at a more complex solution.
Great, thank you, Jim.
Melanie, can you advance to the last slide?
Sure, I think Lucy Liu had a question too.
Go ahead.
Thank you for the interesting presentation. I learned a lot from there, but I do have like a couple questions. The first one is about the model calibration. If I understand correctly, it seems like only the flow model was calibrated. So have you done any calibration for the transport model?
I can take that. No, we did not calibrate the fate and transport model. All of the fate and transport modeling for the sulfate transport was forward modeling. And so that's why we're excited to get field data in to corroborate the sulfate transport model and actually calibrate it. And currently, the results are indicating that the model actually accurately predicted the sulfate transport. So, but that's a great question.
Yeah, typically we would have concentrations to calibrate too, but in this case, because we're predicting something that we had yet to inject, we had no calibration targets for the sulfate transport.
Okay, thank you. My second question is like, I noticed you apply only one recharge zone to the injection area or the pumping area. So what is the rationale there? Like, is only for the like mass balance purpose, or is for the calibration?
That was
Is there
mostly
any
for
like
the, yeah, go.
sorry, like, is there any recharge applied for the other zone, or we only apply this pumping zone?
It was mainly applied for the mass balance, and the recharge basins went into the model where we know them to exist in the real world. There are some observations nearby, so it did affect the calibration. And I think actually those recharge basins proved to be sensitive to the calibration results.
So this recharge rate, I guess, is one of the calibration like parameters, right?
And the recharge rate was based on the extraction rate divided by the area of the basins. So it was calibrated in the sense that the extraction wells were calibrated, the flow rates.
Yeah, because I'm thinking like in reality, maybe it's more mixed, like it makes more sense if we apply like recharge for the whole area.
Yes, we do have recharge for the whole area, the regional recharge, but this was a local area of higher recharge.
So both are not calibrated parameter, right? For the whole area and for this specific area.
Oh no, they were both calibrated parameters. Yeah.
Yeah, in that case, I'm just wondering like why you couldn't combine them into one. You could just apply, let's say, recharge zone 1, recharge zone 2, like several recharge zones. And some of them may be fixed, some of them maybe could be the calibrated parameters. I just don't get like the rationale why we have like overlap recharge applied to this area. Why we couldn't combine them into one.
I think just because it was a focused area of higher recharge. So that's why we just had a zone of higher recharge in that region. But yeah, I suppose they could be combined into one.
Yeah, I mean, like if you want to apply a high recharge in this zone, you could actually increase the calibration rate for this zone only, right? So in that way, you will get a high recharge in this zone.
Sure, yeah.
Okay. Thank you.
Yep. Go ahead, Scott.
Okay, just a reminder to folks, our next presentation on September 8th is going to be with Christy Diller and Jim Liu, and they will be discussing in situ chemical reduction and enhanced bioremediation to treat a commingled TCE and hexavalent chrome plume. Hope everybody can join us for that. In the meantime, we appreciate everybody coming to this presentation. Hope you enjoyed it, and we will close and talk to everyone again in a month. Thanks, everybody.
Thank you.